Let us continue, and let me introduce our final speaker today, Professor Istvan Kovac from University of Primorska.
Thank you, Sasha. And I also would like to thank Elena and Grisha for inviting me to this workshop. So I will talk about two results which I obtained with Istvan Esélyei and Yang-Chuan Feng. And in my talk, all graphs are finite, simple, and undirected. And we say that such a graph is integral if all of its eigenvalues are integers. And I mean the usual eigenvalues. And more particularly, we consider integral Cayley graphs. At this point, I would like to refer to this survey. And this contains many recent results on eigenvalues of Cayley graphs and dry graphs, and also various generalizations of Cayley graphs. It covers many topics. It's more than 100 pages. You can find all sorts of problems, those who are interested in this topic. Here, I will talk results on groups with the following property. All of the Cayley graphs of bounded valency are integral, and these results, the first one was published with my former PhD student. The second one is a new one, and it will be published this year. And our motivation of this research was the following definition. A finite group G, let's call it Cayley integral, if all of its Cayley graphs are integral. So first of all, this is a well-known fact that the eigenvalues for Cayley graphs of a group G can be computed using the irreducible characters. And in the abelian case, the formula is very simple. You go through all the irreducible characters and just compute the character sums. Let's see in examples. So if you take elementary abelian 2 group, then the characters takes always plus minus 1. So the sum becomes integers, and the graphs are Cayley integral. Then if the group is elementary abelian 3 group or direct product of a cyclic group of order 4 with itself, then the character values are not integers, but the set is closed with respect to inverses. And if you evaluate characters on the pairs, inverse pairs, you get integers, and these groups are also examples of integral Cayley groups. Let's see non-abelian examples. The non-abelian example, there's a generalization of the previous formula, which was given a long time ago by Babai. And it says the following: if you have an arbitrary group, and if chi is an irreducible character of degree n, then the graph has n eigenvalues, which can be determined by the following equations. The sum, the k power sum of the values equal to the character sum when you evaluate the character of the all possible k products which you can obtain from the set. Moreover, each lambda I appears n times in the spectrum. It doesn't mean that the multiplicity is n, because it might come from other characters as well, and also might be repeated. We might have repetition there. So you can notice that if the group is abelian, you can also apply this formula, and we just get back the same because every character is of degree 1. So we have a maybe educational example. So I took the quaternion group Q8. So it is its character table. For the 4 one-dimensional, 1 two-dimensional, and for the one-dimensional character, you have the sums always plus minus 1, and this gives you clearly integer eigenvalues. So if you have the two-dimensional character, then you have to consider 2 equations when you take the sum lambda 1 plus lambda 2, and this clearly depends if the central involution is in the set or not, because otherwise it's always 0. And if you make a computation, then for the sum of squares, you have a similar expression. And if you solve it, you can see that this is always integer. The eigenvalues induced by the degree 2 character are also integers, so the group is Cayley integral. However, it's much easier to see this if you just consider the graphs over this group, because up to complementary, you can always assume that plus minus I maximum is in the set, which plus minus I just give you 2 copies of 4 cycles, and if you add the central involution, you just get 2 copies of K4. So it's easy to see that it's integers, but nevertheless, this method can be used to show that the direct product of the quaternion group with an elementary other than 2 group is also Cayley integral. So we have examples also for non-abelian groups, and it turns out, and this was proved by 2 groups independently, that besides these groups which we saw before, there are only 2, basically, there are only 2 small groups which are Cayley integral, and this is the dihedral group of order 6 and the dicyclic group of order 12. And here I also put the definition of a dicyclic group because these dicyclic groups will appear later in the classification as well. Okay, so this is what we know about Cayley integral groups. And then my former student, Istvan, we generalized this, we refined this concept, and we said we introduced the group classes for every positive integer. We say that we introduce a class of finite groups whose Cayley graphs of valency at most k are integral. So you can make some immediate observations of this definition. So clearly we have the chain of classes. The first class is just the first 2 are maybe trivial. The first is clearly just all groups. And this is just because you have to consider here graphs of degree 1, and these are adjoint copies of ages and always integers. So the second class is also trivial to describe, because in that case the graphs are just a disjoint union of cycles, and you just have to be sure that the length of the cycle is 3, 4, or 6. So no non-integer eigenvalue appears, and that means to give you a bound for the order of the group elements. And you have to just think about it that you can get cycles not only for an element and its inverse, but you can also get cycles from 2 involutions. And the length of the cycle is exactly the dihedral group which the involutions generate. And that's why you have to exclude the D8 and D12, these dihedral groups, from the class. So the G1, G2 are relatively trivial classes, I would say. And also note that when we are dealing with this problem, the groups always solvable. It's always 2 free groups, which we have to study. So it turns out, we started to investigate it, and it turns out that actually you can distinguish 5 classes. And the first class is just in the one extreme, when you have all the group, in the other extreme, in the other end of the chain, you have the Cayley integral groups. It's a very, very restricted class. And we proved that in fact, actually, if you look at the classes G4 and G5, they are the same. We will determine also this class, and you have a very prescribed description like G6. And in my eyes, the most interesting is G3. And I will talk about these 2 classes in the next slides. So let's go to G3. So first easy observation or trivial observation about G3, that because there are no, this is a graph. If you have an odd order group in G3, then this should be just an exponent free group, because the number of vertices is odd number, the valency cannot be free in that case. So you just get the G2 class back. However, if you have an even order, then we have this theorem. So in that case, the group is either the dihedral group of order 6, or it can be characterized by this group theoretical property. For any 2 elements, such that one of them is involution, the group generated by X and another element must be isomorphic to one of these groups. And to obtain this result actually can be, it's not so difficult, because we know the classification of all cubic or integral graphs of regular integrals of degree 3. And if you look at this list, there are 13 of them. If you look at the small graphs, you can see just which group actually realize these graphs. So you just have to look at these groups and you get the result. So clearly, to obtain G3, you get a group theoretical problem to handle with. And I will refer to this problem as property P from now on. So property P means this property about two generator subgroups. Okay, so Maya and Wang also proved using this characterization that what are the nilpotent groups in G3. So nilpotent is just a direct product of two group and the free group. And for the two groups, you have this property that the group generated by involution must be in the center and the group must be also of exponent 4. Otherwise, the group is a direct product of a group of exponent 3 with an elementary abelian group. So we will return back. So the second, our main result is a classification of these groups in the non-nilpotent case. But before that, I would like to show you the result for the class G4. So class G4, we managed to prove that in that class, you get the Cayley integral groups and one more family of groups, one more family of dicyclic groups. And when G4 is done, actually, you can get immediately prove that G4 is the same as G5. And just, this is easy because if you take all the inverse closed subsets of that groups of size equals 4, you can see that they generate Cayley integral group. And because your graphs essentially live in this group, they must be integral. And the situation is the same if you just add the unique involution to the set. If you want to have a 5-valent graph, 5-valent graph, you just have to add the unique involution, and the unique involution, with the unique involution, no new groups will appear. So for G4 and G5, you get immediately, and also you can prove that actually G6, if you allow also 6-valent graph, you will get just the Cayley integral groups. And this follows because we will see that these group classes are closed with respect to subgroups. And if you take the smallest subgroups in the family, you can prove that the smallest subgroups, you can find a Cayley graph of valency 6 for that graph, which is not integral. So the essential part was to find G4. And now I would like to show you how we prove that. So first of all, two properties of this class. The first property, which I already tell you, is about closeness with respect to subgroups. And the next property is about closeness with respect to quotients. So the second says that if you have a normal elementary abelian subgroup, then the quotient is always in the class. So the first is obvious because if you take a subgroup, you take a subset, then this is a Cayley graph, and this is always also a Cayley graph of the subgroup. In fact, this is a digit unit of exactly that many copies of this one, and they have the same eigenvalue, so this is clear. For property 2, what we did, we take a Cayley graph of the quotient and we just lift it to a suitable graph, Cayley graph of the group G, so that they have the same valency and also the spectrum is lifted. You can do it many ways, but I would like to show you one way because it might be interesting. And we consider a little bit more general situation. So suppose that you have a graph gamma, and suppose that its automorphism group contains an abelian and semi-regular subgroup. And let Vm, V1, Vm be the representative of its orbits. Now you can define a matrix, which I call connection matrix of gamma relative to this semi-regular abelian subgroup. And actually, you can do it not for abelian, but you can construct this matrix relative to the subgroup and its representative, which contains the entries of the matrix will be subsets. So you take the IJ subset defined by the ages between the two orbits. And in fact, because we have the semi-regular group, it's enough to look at the neighbors of one representatives in the other orbit. And these are, of course, images of VG. So if you think about it, what we are doing is just, it's something like a connection set for a Cayley graph, because we see actually on each orbit, we will see a Cayley graph. So on the diagonals, this is just a connection set of a Cayley graph. And between these two, between other orbits, in non-diagonal orbits, you will see some kind of bi-Cayley graphs, it said. Anyway, the formula for the eigenvalues of such graphs can be extended in the abelian case nicely, and it said that the eigenvalues of gamma are just the eigenvalues of these matrices, and this is somehow relates. It reminds me the matrix of Edwin, because this is sum of root of unities. But if you have to put one element here, you just get a complex root of unities, and this is the Hermitian adjacency matrix. Also have this property. And this is the one reason I wanted to show that. Also the reason that actually this restriction that you have a semi-regular group it is conjecture that every vertex transitive graph has a non-trivial semi-regular subgroup. So it's not very, this condition is not very restrictive. Okay, so let's go back to our aim to prove that if the group is in class GK, then also the quotient group is in the class GK. So we take an inverse closed subset in the quotient group, and we want to show that this is integral, provided that the group was in GK. And it's easy to see that in that case, you can take an inverse closed subset, R of G, which has the same size as S. And in fact, the corresponding cosets give you S. And then you just extend this subset to coset representatives. And now we can use the fact that the Cayley graph over G has a semi-regular abelian group N, and we can build this connection matrix. And when we have the connection matrix, then you know that for all characters, this matrix has as integer eigenvalues, because these are the eigenvalues of this Cayley graph, which was in G, and G was from the class GK. So for all characters, this is true. So put just the trivial character, and we'll get a matrix with integer, with non-negative integer entries. In fact, this is just the orbits of N is form an equitable partition, and this is just probably just a quotient matrix of this partition. Anyway, so it's enough to show, but we have to show that this is just the adjacency matrix. We have here the adjacency matrix of the quotient, and so here's the proof why this is the adjacency matrix. So the matrix is built by this definition, and remember that now the action N acts as a similar group and acts by Rat multiplication. So these are the representative vertices now. Ri and Rj also group elements, and by definition, they are connected in the Cayley graph if and only if satisfies this condition. And in factually, the set R, Ij are just these intersections. Using that this is a normal subgroup, we can rewrite the coordinate of this set in this form, and using that these are representative containing R, eventually you will get that this is at most 1, and exactly 1 happens that if this coset can be written in this form and rewrite it, it exactly means that these are adjacent in the quotient. So this is adjacency in the quotient. Okay, so we have these two properties. One property is closed with respect to subgroups. The other property is closed with respect to normal subgroups of odd order. And let's start to prove the theorem about the class G4. So the first thing to prove, to consider the P groups. And the claim is that in the P groups, we will get nothing new. We will get either abelian, or we get this Q8 times Z2, which is Cayley integral. And the proof goes like this. Now P is 2 or 3, and because it's closed with respect to subgroups, it's enough to consider minimal non-abelian subgroups. It follows from old classification of Rayleigh that in this case, actually we have 6 subgroups, because the groups is exponent 4. We have the Hiltron group, we have quaternion group, we have 2 groups of order 60, 1 group of order 32, and 1 group of 27. Check all of them, and it turns out that only the quaternion group are in G4. That means for any other group, you can find a 4-valent Cayley graph with non-integer eigenvalues. And then we were lucky because we can apply the result of Yanko, which says that a non-abelian 2 group, all of whose minimal non-abelian subgroups are isomorphic to Q8, this must be isomorphic to a direct product of a generalized quaternary group and an elementary abelian 2 group. In our case, of course, this must be 8, and then we get the result. So the next observation is you can consider the group generated by involutions, and we prove that this group actually is in general, this is not a 2 group, but we prove that if G is not D6, then this group is a 2 group. Moreover, it's contains in the center of the group. And this comes right away by the P property. So you take involutions, you just have to take what they generate. And you can see that they always generate an abelian group, so they commute with anything except if they generate A4. But we are lucky enough because A4 is not in the class. You can have graphs, foreground graphs on A4 which is not in the class, so we get the result. The next lemma, which is the last lemma before the proof, is that the group has a normal 0-3 subgroup. It's not a 2 group. And let's see how we just use induction. So let's denote by G3 a 0-3 subgroup and M be a maximal normal subgroup. If then the index is 2, you get right away the induction condition. If it's not, then you have 2 cases. Either 3 divides M or not. If 3 divides M, you use induction again, and you use the property that the quotient is normal in G, and so it's normal in G. What is left is that this is index 3, but M is a 2 group. Then you have to think about what is M. So M may be elementary abelian, but if elementary abelian involutions are in the center, you have a direct product and you are done. So G3 is normal in G. If it's not, you can find an element of order 4, and you just have to show that the group with this element of order 4 and G3 generate a group which contains this SR23. And we are lucky enough that because SR23 is not in G4. Okay, so we can prove our theorem. So we want to show that what are the groups in G4. So we can assume that G is non-abelian, not a 2 group, not is isomorphic to D6. And under this condition, and the previous lemmas tell us that we can write our group as a semi-direct product when I denote by GP the 0P subgroup. So first of all, G3 is elementary abelian because this is about our result about P groups. So P group is either abelian or the quaternion with the elementary abelian. So this is the first observation. And G2 has exponent 4 because if it would not exponent 4, then it would be a direct product. So you take an element of order 4, and since no element of order 12, you can see that U acts on G3 by inverting the elements. And using this condition, it follows easily that you have these groups as candidates. Now, you look at these groups and you just prove that for this group, the size of atmos 4 generates a Cayley integral group. And this trick, as before, tells you that any graph of valency 4, because it lives in a Cayley integral group, it must have integral spectra. So these groups are fine. We prove that they is in our family. Sorry, this should be dicyclic. So the cyclic groups are fine. And now we just have to handle the other direct factor and deduce that M in 0. And we just show that to deduce that it's enough to show that just to study just one small group. And this is not in G4. So by this, we managed to prove that, managed to find G4. So if you go, our next goal was to classify or to study the groups in the class G3. So all the groups whose Cayley graphs of valency atmos 3 are integral. And there were problems here. So the problems you can see, for example, before this SR23 will be in G3. So that was, you cannot use this approach. And also A4 is in G3. You cannot use this approach. So it was much more complicated than this class G4. And actually, this is our classification. And I used a group theoretical term. So because actually this is equivalent for nilpotent case, is equivalent to classify groups which has this property P. So in a sense, this is a group theoretical problem now. And we managed to prove that these are exactly the following classes. So we have the cyclic groups which we saw before, and we have other three classes. The next one is a semi-Dirac product with a Dirac product U times V and a cyclic group of order 3. Then this generator normalizes both U and V. With U, it generates a group of exponent 3, and with V, and V acts on the following way. V can decompose into n Klein groups, and on each Klein group, it generates A4. In class C, we get Frobenius groups when the Frobenius Gerner is a 2 group of exponent 4, and class 2, and satisfy this extra condition. And the Frobenius complement is isomorphic to Z3. And class 4 is very similar to class B in my eyes, and it's also clear from the proof why. It's a semi-Dirac product of a non-abelian special 2 group with a cyclic group of order 3, plus a direct product with an elementary abelian 2 group. And also, we have this extra condition that the centralizer of Z in U is exactly the group generated by involutions in U, which is the center of U. And like here, we have this decomposition of V. No, we don't have it, but we can write a product of U as a product of the center with n subgroups, and this n subgroup satisfies the following conditions. We have this normality condition. Every subgroup is isomorphic to the quaternion group, and every subgroup together with the generator of the cyclic free group generate as a 2 free. So these are the classes, and we also studied a little bit further these classes. So the first is clear. The second is also sort of clear, I think. And for C, we get the following result. So the Frobenius group in this class, we managed to prove that the kernel is Q83. And Janko studied also the case when the only possibility for a minimal normal subgroup is this group H of order 16, this group of order 16. And using this classification, we managed to prove that in the class C, if you assume that the group is also doesn't contain this minimal normal subgroups, then there's only unique possible Frobenius group, and the order is 3 times 2 to the 6. Besides this, we also played a little bit with magma, and we found further 2 groups in family C, further 2 small groups. One is order 3 times 2 to the 8, the other is 3 times 2 to the 10. And that's all what I can say about class C. And class D is more interesting, I think, because we have here an interesting example. Actually, we found 2 infinite examples. The first example comes from the special unitary group of dimension 3 over a finite field of Q elements when Q is an odd power of 2. So if you write the 0,2 subgroup, this is the matrices which you get. And it turns out that the 0,2 subgroup is a special group. The center corresponds exactly those when A is 0, and this is an elementary abelian 2 group. And if you take a diagonal matrix, when you put lambda 1 and lambda in the diagonal, and lambda is a third root of unity, which is not 1, then this Z will normalize this group, and the centralizer will be exactly the group generated by the involutions. And this is exactly what we need here. So we get that these groups is a family, all these groups is family D, and the order is 3 times 2 to the 6 and plus 3. So we get an interesting family. And this is somehow, it's interesting because you start with an innocent question, drawing these cubic graphs, there are certain them, and you can get, in the end, you can get the special unitary group. The other example, we constructed ourselves. And this is the construction, this is the definition. I don't want that you read all the relations, but I can explain in the picture. So the group is generated by AI, BI, and CJ. We have A, B, and C generators. And what we are doing that we glue together quaternion groups. So AI, so you can imagine this picture, that this picture contains the nodes represent the generators AI and BI. So this is A1. I didn't have time to write it. So this is A1, this is B1. A2, B2, A3, B3, and so on. So the node represents these generators. These on the edges, on the horizon, on the vertical edges, you get a quaternion group. So these are standard generators of the quaternion group. And these are the other edges. You put the commutator of these two nodes. So this is A1, this is B2, and the commutator is C1. Again, this is B1 and A2, and the commutator is C1. So this is the C1 commutator. This is C2, and so on. And everybody, so C1, C2 commutes with any elements, any generators. And if you don't see an edge, then the corresponding generators also commute. So in a way, we just glue up together quaternion groups. And in the end, we managed to get this group will be also a special 2 group of order 2 to the 4 n minus 1 if you join together n quaternion groups. And the automorphism of order 3, which acts on in one quaternion group, can be extended to an automorphism of the whole group of order 3, such that it fixes or centralizes exactly the group generated by involutions. And because of that, this is also an example in our family. Okay, so we have these examples, and now let me talk about how to prove this theorem. So just recall that this is a property P, and I also let me recall some consequences, which most of them we saw before. So this property implies that we have a group whose spectrum is very restricted, and in particular, this is a solvable group. And also, we know that if we have two elements and one of them is involution, they not, because of this property, they not commute if and only if the other element is order 3, and because they X and Y generate the alternating group, we have that these are actually the 3 elements in the claim group, and the product is 1, which we use. And also we use that any two involutions in commute in G. The involutions pairwise commute because of this condition. And we also had this condition that the CeLO2 subgroup, because it's in the family, should satisfy this condition. So the CeLO2 subgroup, the group generated by involutions, must be contained in the center. The CeLO3 subgroup should be exponent 3. And now you can also prove that these groups are, this with property P is actually closed with respect to taking quotients. And you can prove it just using property P. You don't need a graph for that now. So these are the basic property which we are going to use in the proof. We have some other properties, other information about the groups, which is you maybe not so, maybe they don't come so quick. So the first, so from now let me denote by J a group having property P and GP just a CeLO-P subgroup. And the first observation which you can make is that the group generated by involutions in G is exactly the omega-1 G2 group, which is elementary abelian 2 group. And also we have these relations. So the derived subgroup is contained in the fractini, contained in the group generated by involutions, and contained in the center. The proof is I write here because it's not so complicated. So we just use the property, and you see the involutions are commute. So what they generate is a 2 group. And because it's normal in whole G, it should be in the CeLO2 subgroup as well. And in fact, it should be the omega-1 2 group in the CeLO2 subgroups. So these are the CeLO2 subgroup, but in the CeLO2 subgroups, any involution is commute. So because they don't commute only with elements of order 3, so this omega-1 of G2 must be in the center of the CeLO2 subgroup, and we get the first part. To get the other part, take an element of order 4. And this equation tells you that if you quotient that by omega-1, 2, you get an elementary abelian 2 group. And because of that, this group should contain the fractini subgroup, which contains the Theorem subgroup. So you just finished. If you write this together, you will get exactly this chain of relations. The next information is the following. So suppose that the largest normal few subgroup is trivial, and suppose that G2 is of exponent 4. then you can prove that in that case, the largest normal two subgroup in G must be strictly larger than the group generated by the involutions. Okay, let's prove first this. So then you use the fitting subgroup, because omega 3G is 1, the fitting subgroup should be omega 2G. And in that case, you can see that because this omega 1G2 was the center of the CO2 subgroup, you can get this condition. So the centralizer of this one contains the CO2 subgroup, so you get this condition on one hand. On the other condition, the centralizer of the fitting is contained the fitting, and you will get this other relation, and that would constrain the fact that G2 is of exponent 4. Moreover, the second lemma says, actually, and we combine these two lemmas. So the second lemma says that if omega 2G, so the largest normal 2 subgroup is strictly larger than this group, and G is not a 2 group, then G3 must be free. Moreover, G3, the action of G3 on this normal subgroup by conjugation induces a regular group of automorphism of this quotient. So that means fixed point 3, every element is fixed point 3. And to prove this, we first observe, we take an element from G3. This is a folder 3 element because the exponent condition and the centralizer of G in the quotient is just an image of the centralizer in G. And using the fact that no element of order 12, the centralizer cannot contain element of order 4. So the centralizer contained must be contained in this group, but that means this is a trivial group. So on the quotient, we have a fixed point 3 action, and we are done if G3 is 3. If G3 is not 3, because the group is exponent 3, if the order would be larger, then the group would contain an elementary abelian group of order 9. And we use a property that the centralizer of a non-cyclic abelian group, or if you go through the centralizer of the elements of a non-cyclic abelian group, non-trivial elements, these must generate the whole group. In one hand, in the other hand, all of these lies in omega 1G, and you have this relation, but this is impossible because we assume that omega 1,2 is still larger than omega 1 of G2. So this is information which we also need from these groups, and actually we will combine it. So you can see that basically what you can say that whenever these conditions satisfied, you can immediately say that G3 is 3, for example. Okay, so let's start the proof of the theorem. So from now on, G is a non-nilpotent group with property P. So first of all, it's not hard to check that the groups in these families have this property. So I will not bother with that, but I will speak about the other direction. And so you want to show that if the group has the property P, then it must be one of the families. And first, we analyze the case when the group has a normal 0P subgroup. The easier part was the case when this is a free group. And if this is a free group, and if the 0,2 subgroup would be elementary abelian, then this would be exactly equal to this normal subgroup. And because the 0,2 subgroup is normal and G3 is normal, then your group would be an nilpotent one, and this is impossible. So you just take the case when G2 is of exponent 4. If G2 is exponent 4, we have a normal free subgroup, and we just use the same idea which we used in the previous proof when we studied the class G4. So you have a normal free subgroup, you have an element of order 4, and the action on G3 must be fixed point 3, and you can get the dicyclic groups. The next case is when G2 is normal in G. So in G2 in normal G, you can make a simple observation, which we call all or none lemma. It says that if you take any element of order 3, then its centralizer either no element of order G2 or centralizes all element or involutions. So this is what it says, and this comes from the property, from P property, because if it's not true, then you can find two elements, two involutions. One is commute with Z, the other does not commute with Z. The one which is not commute generate A4, and because of that, you can make a two-generator group which is A4 direct product Z2. One of them is an involution, and this is impossible because this violates the P property. The only non-abelian group, two-generator non-abelian group must be A4. So this is impossible. Okay, so G2 is normal, and the first case to consider is when G2 is elementary abelian. Then we have elementary abelian. You take the centralizer of this elementary abelian group in U, and by the all or none lemma, the centralizer should have index 3. And because of that, you can write G3 generated by U and Z acts fixed point freely on this elementary abelian group. And because of that, if you can write it, you can decompose V as for Koenig subgroups. And we conclude that you precisely know the action on Z on V. And because of that, you just conclude that the group, but in this case, just the group is in family B. The other case is when G2 is exponent 4. In that case, you can immediately see that the largest normal 2 subgroup, the G2, is strictly larger than the group generated by involutions. And by the previous lemma, you will get that G3 is order 3. So you actually have a similar group with a cyclic group of order 3. And now you have again two cases by the or lemma. In the first case, you get exactly the condition that you get a Frobenius group in family C. In the second case, with a bit more work, it's possible to show that G is in family D. I don't want to go to the details. It was a little more complicated, but it's not so difficult to prove that in that case you have family D. So we get all in this way. Analyzing the normal subgroups, we get all the families. So what is left to show is that either G2 or G3 must be normal. And that was the tricky part. And we argue by contradiction. I assume that this is not the case. So I will skip two lemmas, which is quite technical, and I don't want to show it here. But I will just go to the end of the proof. So after these two lemmas, we can assume that we arrived in the following situation. So G2 is exponent 4, G3, the zero free subgroup is of order 3, and also the largest normal subgroup has index 2. The largest normal subgroup, 2 subgroup has index 2 in G2. So let's write G3 generated by Z, and let's write N to be the normalizer of G3 in G. Then, as before, we saw it before, it's not difficult to show that in that case, two cases can happen. N is either a direct product of G3 with an elementary abelian group, or it's a dicyclic group. But the first case is not possible, because in that case, the centralizer of G3 would be the same as the normalizer, and that would mean the group has a normal 3 complement, which would be G2, and this is not possible. So the second case is possible, and because of that, we can find a W in G2 such that W and the generator Z generates a dicyclic group. I color this W because this will play important role in my proof. So I would like to, I'm hoping for a contradiction, and I'm just collecting the important elements which will actually give me the contradiction. So we have this W, and note that because this is a dicyclic, actually this W inverts Z. Now let's study further this W. So let us denote by U the largest normal 2 subgroups. If W will be in U, then you could show that because U is normal, and also this inverting property, that would be imply that the commutator element would be counted into intersection, which is not possible. So that means this W is not in U, but U has index 2 in the zero 2 subgroups. So if you take the group generated by U in W, actually, this is a Silo 2 subgroup of your group. And this group has property P, and we also have this property about the Silo P subgroup. So we can use here now for P. So P satisfies the condition that the commutator is contained in the group generated by involution, which is also contained in the center. And if you rewrite this property, you can get the following condition. For any U in U, if you write a conjugate, the result can be always written as U times an involution from the center. So because this is a commutator, and because of this condition, this must be in the center. And because of here, this must be an involution or maybe identity. So for any U in U, conjugating by V, the result is always U times an element of atmos 2 from the center. Okay, now let's continue. So omega, the largest normal free subgroup, is trivial because the Silo of this subgroup is of order 3, and the Silo of this subgroup is not normal in the group. So the largest normal free subgroup is trivial, and one of the first lemmas we had, if this is trivial, then the largest normal 2 subgroups should be strictly larger than the group generated by the involution, which is elementary billion. And because of that, this is exponent 4, and we can choose now an element U of order 4. So this will be the other important element. And the last important element will be its image under the conjugation by Z. Okay, then one more thing, because we start the contradiction, that you can observe that it's not difficult to show that this U times UZ times UZ square is equal to some element from this subgroup, which is from the center. And by this notation, this is just V, and this is just V to the Z. So in fact, you have this equality. And also recall that we already found some W from the Silo 2 subgroup, which inverts Z. So we have this W, we have this V, and so we have W, U, and V. And now we can start playing with these guys. Okay, so what do we have? So what we have is that, first of all, using this, we can see that VZ, V to the Z, this conjugate always can be written as UV times X1 when X1 is from the center. Now we use this property, we apply this property from U and apply this property for this element. You can also say that U to the W is U times V1 when V1 from the center. And also this is a product of the same element times Y2 from the center. Using this, we can compute the following. So if you take U times V times X1 times Y times to the Z minus 1, let's compute this. And let's use the fact that Z minus 1 is just the same as the conjugate Z to the W. Okay, now this is actually, you can apply first, you can apply V inverse here, and you apply V inverse here, you will get this element from that equation. So this is what you have here. Now, if you apply, this is nothing else that V to the Z, so what we get is V to the Z squared, but V was the image of U here, so this is just U to the Z3, but Z3 is identity, so this is U W, which is U times Y1. Okay, we are almost done. So what you have to take, you have to just take the conjugate by Z to the two sides. So so for this side, if you take the conjugate by Z, get U to the Z, which is V, and Y1 to the Z, and this time you will get U times V times X1, Y2. If you rearrange it, you will get this equation. Y1 to the Z is equals to U to the V times X1 times Y2. And recall that Y1, X1, Y2 all are from the center and all are of order atmos 2. But what we get here? We get here that this is an element of order atmos 2. But these are elements of order 2, atmos 2, order atmos 2, and they are center and use of order 4. So on the right side, you get an element of order 4. On the left side, atmos 2, it's not possible. And this shows that in the group in this group, it should have either a normal Silo 2 subgroup or a normal Silo 3 subgroup. In both cases, we just determine we just get the classes in the theorem. And this is the proof of the theorem. And actually, this is the end of my talk, and I will just say thank you for your attention.
Okay, thank you very much for your nice talk. So does anybody have any questions or comments? We can't hear you.
Sorry, I think I missed part of the last theorem. Can you please go back to that slide where you posted the theorem?
The last theorem?
Yeah, with the long proof, yeah.
This one, I suppose.
Yeah, actually, that's what I wanted to see, yeah. Thank you. Let me have a look. So that is also in the archive, so that I can have a look there.
I will put it, not yet. I will edit, yes, I will put it there.
Oh, then I will see that then. Thank you.
Yes, I will do it.
Okay.
Nice result.
Thank you.
So any other questions or comments? So I may have a naive question. You consider Cayley graphs with symmetric connecting sets, right?
Yes.
So what can be done, or what can you say about like general Cayley graphs? Is there any results? Are there any results?
Digraph?
The digraphs, yeah, digraphs.
I don't know. It's yeah, that's a good. I'm not sure that it's. I think it's very different, I would say. It's a very different situation. I mean, yeah. For example, if you just take a directed, probably you will get nothing interesting because it's too restrictive. In that case. So even if the order is free, you can get a directed free cycle, which is if you this is another integral eigenvalues. So probably it's not really you cannot get interesting results here.
Well, if you consider ordinary adjacency matrix, but if you Edwin on Monday was about many options how to choose adjacency matrix for a diagram, but it's just I understand.
Yeah, it's also you can consider other eigenvalues. I know that there are people who are consider the situation for Cayley graphs, the same problem for Cayley graphs. So that means you have not a regular group, but instead of a regular group, you have a semi-regular group with two orbits.
Two orbits. Yeah.
And two orbits, and for two orbits, if you have the set not necessarily inverse closed. If the set defining the edges between the two orbits, it shouldn't be inverse closed. And then I know that Iranian mathematicians work into this direction.